All right, so streaming has started, and as I said, today I will be showing you or telling you the most important topics that you must focus on for quiz 2. Okay.
Sir, one doubt.
Yeah. Yeah.
Sir, syllabus is from week 4 to 8 or 5 to 8?
It's from week 5 to 8, but nevertheless, it always includes week 1 to 4, right? So
Okay, sir.
everything is interconnected, right? So
Yes.
whatever you did from week 1 to 4, we just did the same things, all the things, more or less all the things in higher dimensions. So it doesn't impact. At least for math 2, it is always the same. It's like span, right? If you say span week 5 to 8, week 1 to 4 will also be in that set. All right. So, but primarily we say it is from weeks 5 to 8. So you can take it. All right. So I hope my screen is visible. So the agenda is very simple. I will just tell you the most important concepts that are important for quiz 2, not in your future courses. Okay. So this particular session emphasizes more on quiz 2. And after that, if you have any doubts in those concepts, if you still feel something not clear in any of the topics, let me know. I can discuss them briefly. And then if you have any doubts in mock, we can discuss that. Or if you have doubt in some concepts, we can discuss that. In some problems, we can also discuss that. Okay, so that's the idea. But we will start off with the concepts which are most important or to be revised for quiz 2. Okay. So yeah, definitely you should know what a span is, right? So given some vectors to you or one or two vectors to you, you should know which all other vectors can be spanned using these vectors. So that's what span is. And span membership is given any vector, you should be able to tell whether that particular vector is a member of the span or not. So that is very, very important. And this is week 5. That's where we start week 5, right? And this is for higher dimensions. Okay. So for R2 and C2, it's very easy to check, right? But when it comes to higher dimensions, you need to know some techniques, right? Given two vectors or three vectors in R5 or R10, how do you check a new vector belongs to the span of these two vectors or not? So that's a very important skill or the concept that you have to focus for quiz 2. Okay. And next thing is, of course, linear dependent and independent. Given a set of vectors to you, you should be able to tell whether those vectors are linearly independent or linearly dependent. Okay. So the conditions that you have to check or write them in a matrix form. The most easiest way is or convenient way is to write the given vectors, each vector in each row, and then try to convert that matrix to into the row echelon form, right? Use that row echelon form and convert that matrix to reduced row echelon form, and then see whether there are any zero rows or not. If there is any zero rows, then it's linearly dependent. If there are no zero rows, there are no rows that are completely zero, then all the given vectors are linearly independent. So that's the easiest way, which I follow. And I think for most of us, that's the easiest way to check whether a given set of vectors are linearly dependent or not. And next comes, these are technical terms you should definitely know when you say you know linear algebra. They are basis, dimensions, right? So basis and the dimension of the space and the subspaces also. So given a subspace, you should be able to tell how many vectors are required to generate the whole space, right? That's sort of dimension. And what are those two vectors put into a set? That's the basis, right? So these computing basis and dimension. Dimension is like number of vectors in the basis, right? So it's okay, but coming up with basis for any subspace is a serious skill that you have to develop, at least for quiz 2. And these, most of them are useful for you in future courses also. When you say somebody that you have learned linear algebra, then definitely people will primarily ask you whether you know span, whether you know basis, whether you know dimensions. So these things are very, very important. And also in future courses, wherever linear algebra appears, you will definitely encounter this terminology. So knowing this is important. Also, finding this is equally important. Okay. And the next thing is the linear transformations. Now in higher dimensions, not just with 2 cross 2, in maybe not beyond 5 also. So if we go beyond 5, then obviously we know that it computations takes more time, and quiz 2 is time bounded. So therefore, again, we were also bounded between 3 to 5. So not beyond 5-dimensional spaces and not below 3-dimensional space. Okay, so most of the questions you are going to see will be in between. And even linear transformations also, when I meant higher dimensions, I meant maybe 3, 4, 5. 6 is very unlikely. Okay, 6 also you can include, but it's most unlikely. Okay. If we want to be so cruel, then we go beyond 5. Okay. And once we learn linear transformations in higher dimensions, and we will also look into the range, null of all of the linear transformations, and everything comes in that linear transformations in higher dimensions. Okay. So once you learn linear transformation, definitely you should know the range space and the null space. Okay. So you should be able to compute the range space and the null space, everything that. And the next thing is, after doing range and null, the next thing we look into is the eigenvalues and eigenvectors of a linear transformation. So eigenvalues are very, very abstract concept to understand it, but in a simple terms, when you input something to your linear transformation, if your output is just the scaled version of your input, then the scaling factor is what eigenvalue is, and the input which you have given is what the eigenvector to your linear transformation. If you have to understand it in very simple outer way, if you don't want to dwell into the technicalities, if you want to look what are eigenvalues and eigenvectors of a linear transformation in an outer space, then it is like when you input something to this linear transformation, if the output is just a scaled version of your input, then how much is it scaled is what eigenvalue, and the input and the output, the input is what your eigenvector is. As simple as that. And you have to practice more and more problems on this. So given a linear transformation to you, whether in matrix form or just the function form, it's like t of x comma y given as something. So in both the ways, you should be able to compute eigenvalues and eigenvectors, and that is also very, very important. Okay, so I think with this, weeks 5 and 6 mostly covers these things. Okay, so the first 5 points are for weeks 5 and 6. So focus more on these concepts first, solve problems related to this. And from week 7, you should definitely know the inner product. So given two vectors to you, whether in real or in complex, you should be able to compute the inner product. And given a vector to you, you should be able to compute the norm of a vector. Norm is basically the distance from the origin to that particular tip, vector tip. Okay, so that's norm. So the distance from the origin to the vector. Okay, so that's norm. And of course, you should practice problems related and in and around of this inner product norm. And there are many things, right? Like, uh, um, so what's that? So there are a couple of inequalities and orthogonality, definitely. Like if two vectors are perpendicular to each other, then both the vectors are orthogonal to each other, right? Orthogonality with what's the connection with inner product? Anybody? So when I say two vectors are
So
orthogonal,
Zero.
that means the dot product is 0.
correct. Exactly true. So if V U is 0 implies V and U are
Orthogonal.
perpendicular, or we say
Orthogonal.
V and U are orthogonal. Orthogonal. All right. So those things, practice problems related to this. Well, I think one of the mock question is also, you would have seen one question in the mock using this inner product norm and thing. And the next thing is Gram-Smith orthonormalization. Okay, so this basically generates an orthonormal basis from a normal basis, right? So this is a method where you input any basis of a space, it will output you the orthonormal basis, right? So orthonormal, so it should be, each vector in the basis should be of length 1, as well as all the vectors in that particular orthonormal basis should be perpendicular to each other. So that's orthonormal basis, and Gram-Smith orthonormalization exactly does that. You give any basis, it will just give you, the output will be an orthonormal basis, and you should know how to compute an orthonormal basis from a given basis. Okay, and moving, the next thing is to solve problems related to this least square solutions also. Even here we kind of use, you can directly use the formula that is always there, but you have to use the idea of projections, right? So projections, least square solutions, and for quiz 2 at least, you can directly focus on least square solution. Okay, so you should be able to compute the least square solution to a given matrix A and B. Okay, and also again, mock has problem related to this. Try solving that and some more problems if you want to get more experience on this concept. Solve more problems. Okay, and so still here it's week 7, I assume. And in week 8, basically, Rees representation is one thing which connects an operator to its adjoint, right? So that is obviously important, but just go through it once. Okay, and the next most important thing is this 4 fundamental subspaces, right? So range of T, null of T, range of T star, and null of T star, where T star is the adjoint of an operator. Okay, so these 4, given a matrix or again a linear transformation to you, you should be able to compute these 4 fundamental subspaces. Once you compute these 4 fundamental subspaces, obviously you should be able to come up with a basis for each of the 4 fundamental subspaces as well as the dimensions, right? So that is also important. And the next thing is right and left vector eigenvector. Excuse me. Right and left eigenvectors of an operator. You should know how to compute right eigenvectors, which are normal eigenvectors, but left eigenvectors are slightly different and confusing. Just go through it once. Not that important, but just go through it once. Okay. And the last thing, which I just wanted to have 10 important points, but this is also important. Solve problems related to this self-adjoint. Okay. So self-adjoint operators are where T is equals to T star, which is very, very special. Not that easy to find. Okay. So solve problems related to this also. Okay. So these are the major important concepts. Again, special mention. This is only for quiz 2, not
Oh, yeah.
for. So we will tell you what are the course outliers at the end of the course. So what all things you should definitely know before moving forward from this particular course. Okay. So this is majorly on quiz 2. All right. As I stated, please focus on these things. Another. Okay. So this is one thing I missed. Definitely, again, this will haunt you. This would have haunted you in quiz 1. This will all again haunt you in quiz 2, which is diagonalizability. Diagonalization, basically. So, what diagonalization is? Given any matrix to you, or again, linear transformation or matrix, both are there is a one-to-one correspondence, right? So, given a matrix to you, I can always find a linear transformation. Given a linear transformation, there will exist a matrix. So, given a matrix to you, you should be able to decompose this matrix into product of 3 matrices, where the D which is sitting at the center is an is a diagonal matrix, and P is a matrix which is anybody?
The given matrix?
So how do you diagonalize this? So any matrix A, this P, D, P inverse, you should be able to decompose. Okay, not any matrix. A should be diagonalizable, only then you can do this. Okay. How do you do this is D is basically a diagonal matrix where the diagonal entries are eigenvalues. Right. So lambda 1, lambda 2, lambda 3. How do you find P? What is P?
Eigenvectors in the account.
Correct. Exactly correct. So these will be the eigenvectors written in column wise. Okay. So don't write vectors in row wise and say this is my P. So P is the eigenvectors written in the columns, and D is the diagonal matrix where diagonal entries are just the eigenvalues. So yeah, I think these are the most important concepts. Again, solve problems related to these concepts so that your quiz 2, getting high scores in quiz 2, will have higher chance. Okay. All right. So my first agenda is done. So the next one is, if just whatever the concepts that I have emphasized here, if you have any doubts in any of the concepts, let me know. We can have a discussion. Or if you want me to solve any problem related to this, if you have ready-made problem, you can just give it to me. Or else if I have to come up with a problem, then I will take 1 or 2 minutes to just find a problem and solve.
Excuse me, sir.
Yes, Vishal. Yeah.
It's not specifically a topic or a problem related to these concepts. So
Okay.
during the last session also, I just wanted to, since it was really late, I just wanted to ask sir that what are the chances of this topic coming? That is circular convolution and circular matrix. Is it important for this quiz?
So those are the applications of linear algebra, right? That is like week 9, I suppose.
No. It's in the end of week 6. Circular convolution and circular matrix.
Oh, okay. It's coming in the week 6.
Yeah.
Oh.
So since I haven't understood what sir has taught in that, and I found it really hard. So
Okay.
just a doubt that are there any chances of that topic coming into this?
All right. So at least for quiz 2, you got saved.
Okay.
Okay. So that's like an application. So that we will come to that in the end term or by the end of the course. Okay. So in quiz 2 is more on math perspective. It's like making you understand what linear algebra is. Quiz 1 and quiz 2. End term, we will focus on the applications of linear algebra. Primarily, our focus will be on that. So during that, of course, circular convolution is very, very important. Okay. So because again, you are going to be an electronics and electrical engineer, right? So this sampling. So if you have done courses like signals and systems or DSP, especially, you will see this convolution, circular convolutions coming into the picture. Okay. So at least for quiz 2, I can assure you that you got saved, man.
Okay. Yeah, sir. And yeah, please go.
Yeah, so that's it. So don't ask me whether that from now on, don't ask me whether this concept will come or that concept will come. Rather, I can tell you these concepts are most important. Okay, so from that you should be able to sense few things. Okay. Sorry, Venkata Subhash.
Sir, I just joined.
You just joined.
He wasn't supposed to be here.
I know him. He's your senior.
Yes.
Yeah. So you just joined, is it?
In every session he joins.
Hey,
For
no,
no use.
Okay.
no, I just joined. I was just done with my session and randomly
Okay,
found
so
this link.
you just wanted to see what's happening in this session, who is taking, or you just wanted to give them hints. Okay, anyway, since you joined, let me make use of you. Just tell them how you prepared for quiz 2 and tell some tips to them who joined, right? That will help them.
For me, at least, quiz 2 went smooth. End term was the thing which got tensed up.
Okay.
Because
Okay.
quiz 2, most of the concepts are repetition from quiz 1. Just we will be extending the dimension.
Right. And just look at the board and see whether I have mentioned all the important concepts or did I missed anything.
Sir, honestly, I forgot everything. As you said, every time once you have to work with linear algebra, we have to revise the notes for sure.
Yes. All right. Thanks.
Yes. Sorry for disturbing that.
Oh, that's fine. All right. Yeah, so let's move. And as I said, if you have any doubts in this, you can let me know. Or else then we can move to the final agenda, which is doubts in quiz 2. Mock 2. So I hope most of you have solved mock. If not, again, that's a double star to you.
Sir, I will in the night only. I was trying to complete all the weeks first.
All right. So now you see there are 5 stars on. Please do solve mock.
Yes, sir.
Okay. So it's like a 5 star. So that important. Solving mock. So solve it. If you are unable to solve any of the question, just get help from your friends or whatever. Do it before Sunday. Okay. After Sunday, you'll just regret. I can tell you this also. So you will feel like, अरे solve करना चाहिए था. You will feel like this.
Yes, sir.
Okay. So let's not get into that scenario.
Yes, sir.
Rather try to solve mock for quiz 2 and that will also help you for your preparation.
Yes, sir. If you face any problem, we have GSpace already.
Yeah, you can surely contact us via GSpace. So since I have many spaces, unless you tag me, so I will not be able to see. But anyway, tomorrow I will definitely be active because that's when students get more doubts, right? As exam comes near and near, doubts will start increasing exponentially. So yeah, so I will be there. All right. Anything else? So I think even in mock also it's fairly straightforward questions. Nothing new. One question I think most of you will slightly struggle, which is the second question. Like it's about the nilpotent operator. kind of t power 4 is equals to 0. So most of that is also not that tricky, but that is one question which which you would have seen for the first time. You wouldn't have seen in the activities or graded, but that can also be done. So that is also okay. Yeah.
Sir, can you
Anything?
please have a look at the 8th question once?
All right. Let me just look at the 8th question. Can you just tell me the question starting, please, so that I don't have number.
It's a 3 by 3 matrix, and we have to find the diagonal matrix D and an invertible matrix P,
All right, all right, all right, all right. Got
yeah,
it.
such that B is equals to P inverse.
Okay. So let me see. Is this a question? B is 1 minus 3 0 minus 3
Yes,
1 0 0 0 minus 2.
yes, sir. Exact.
Right? Yeah. All right. So let's do this. So the goal. So always for any problem that you are going to solve, it's better to have a final goal or what the question is asking you. So the question is asking us about the diagonal matrix D and the invertible matrix P. Okay. So what we have to do is we have to decompose this B into P into D into P inverse. And as we know, D is basically a 3 cross 3 matrix with diagonal entries as the eigenvalues and all other entries will be 0. And P will be a 3 cross 3 and each column will be the eigenvector. So lambda i's are eigenvalues and vi's are their corresponding eigenvectors. Okay. Again, this is also important. So v1 is the eigenvector for lambda 1, not for any other lambdas. Okay. So let's try to do this. Now our problem has moved from finding D and P to finding the eigenvalues for the matrix B. So now our goal has been changed. So how do we find the eigenvalues? 1, minus 3, 0, minus 3, 1, 0, minus 3, 1, 0, 0, 0, minus 2. So how to find the eigenvalues of this? So we'll take the determinant of, so there are many methods again. So
Yes,
best and the easiest way is take the determinant of B minus lambda I and equate it to 0. Correct? Which will give us an auxiliary equation. So if I do that, this will be determinant of 1 minus lambda minus 3 0 minus 3 1 minus lambda 0 0 0 minus 2 minus lambda. Correct. Yes. And the determinant of this will be minus 2 minus lambda into 1 minus lambda whole square minus 3 into minus 3. I hope everybody understood this step, right? So I just took this times this into this minus this into this. That is sufficient. So because the others are zeros anyway,
yes, sir.
this will be the determinant of, right? So if I simplify this, minus 2 minus lambda, and this will be like 1 minus lambda whole square minus 3 into minus 3 will be 9, and 9 I can write it as 3 square is equals to 0. So this will again be minus of 2 plus lambda, and the inside is a square minus b square. So I can write it as 1 minus lambda minus 3 once, and it is like a minus b into a plus b. Okay. So 1 minus lambda plus 3 is equals to 0. So from this I can sense that lambda is equals to minus 2 is one eigenvalue. And from this This will be, okay, let me do. So this will be 2 plus lambda into, this will be minus lambda minus 2, right? And this will be 4 minus lambda is equals to 2, is equals to 0. So we will have lambda is equals to minus 2.
Lambda is equals to 0.
Lambda is equals to 0.
I got, okay, minus, I got one lambda as minus 2.
Uh-huh.
And
And the other lambda 1 will be minus 2, lambda 2 will be minus 2, lambda 3 will be 4.
oh,
So
yes.
this is what I got.
Yeah.
Maybe the calculations you should check.
Maybe I might have made mistake.
Yeah, maybe the calculations you would have gone wrong, but
Yes.
this is what we'll get: minus 2, 4. So from this we got our D. D is very easy. So minus 2, put minus 2, 4, 0, 0, 0, 0, 0, 0. Right? So D is done. Now I have to find P. So for P, we have to get the eigen vectors. So for lambda 1 is equals to minus 2. Let's see how many eigenvectors we get. So basically lambda 1 and lambda 2 are the same. Okay, in order to be diagonalizable, the geometric multiplicity should be equals to algebraic multiplicity, which means if I have minus 2 2 times, so my eigenvalue is repeated twice, I should have 2 eigenvectors possible for minus 2. Two linearly independent eigenvectors possible for minus 2. All right, so let us check so that we can get it by checking. So how do I get the eigenvector? You can do the, again there are many things. So you just multiply. You just have to get the null of b minus lambda. Right? So our eigenvector is a vector in the null space of b minus lambda 1. So how do I get that thing? Let's say v is our eigen. So v1 is the eigenvector. So b minus lambda 1 of v should be 0. So that is what we have to see. Right. So b minus lambda 1 will look like this. So lambda 1 is minus 2. So b minus lambda is this. So in this, I have to substitute minus 2. So if I substitute minus 2, this will become 0. Right? So this becomes 0. This becomes 3 and 3. So we will have 3 minus 3 0. This will be 3 minus 3 0. Minus 3 3 0. 0 0 0. And this is v1. And we have to find v1. If I write it as x, y, and z is equals to 0 and solve, I'll have 3x minus 3y is equals to 0, minus 3x plus 3y is equals to 0 from the second this and this. And the last is 0 equals to 0. It doesn't give us anything. Okay. So the eigenvectors, so all the vectors coming from R3, so both will give me x is equals to y. Right. So your first coordinate and the second coordinate should be equal. That's it. So any vector which has first coordinate and second coordinate equal is an eigenvector. So the possible eigenvectors could be both x and y can be 1 and 1 and z can be 0, or both x and y can be 0 0 and z can be 1. Right? So these are two linearly independent vectors where both the vectors satisfy this condition. And both the vectors are eigenvectors. Basically, you take this vector, multiply it with b, you will get the scaled version of this vector. You take this vector, multiply it with b, you will get the scaled version of this vector. Like minus 2 times this. You will get minus 2 times this. Alright, so we got two eigenvectors. And both the eigenvectors corresponds to this eigenvector will correspond to lambda 1. This eigenvector will correspond to lambda 2, which is again minus 2. Okay. So is this clear?
Yes, sir.
Okay. So now we have to find the eigenvector for lambda 3, which is 4. So so that means it will be the null of b minus 4 lambda, and that is b minus 4 lambda of v3 should be 0. So b minus 4 lambda, I have to substitute lambda is equals to 4. If I substitute it 4, okay, so I will get minus 6 here, minus 3 here, and 3 here. Sorry, minus 3 here, right? Minus 3, minus 3, minus
minus.
6.
Yes, sir.
Correct. So that will be our matrix. So minus 3, minus 3, 0, minus 3, minus 3, 0, 0, 0, minus 6. Okay. And any vector that multiplies to this. So I need a vector that multiplies to this and gives me 0, 0, 0. Right. When I said 0, it's like 0, 0, 0. Okay. So if I again multiply and write it in the linear equations, I will get minus 3x minus 3y is equals to 0, minus 3x minus 3y is equals to 0. And the last one is minus 6z is equals to 0. From the last equation, we will get z should definitely be 0. Right. And from these two, we will get x plus y should be 0. So that means our vector should be such that the sum of the first two coordinates should be 0 and the last coordinate should definitely be 0. So one such possibility is minus 1, 1, 0, right? Or if you take x as 1, it will be 1, minus 1, 0. Okay. These two are linearly dependent basically. So you can only take any one of them, not both. Just go look into the options and see. In the options, you can see that this particular vector is given. But anyway, if you just multiply minus 1 to this, you will get this vector. Right. So we can also give this vector, this column in P or this column in P. Okay. So as this is given, this will be our V3. That's
Yes,
it.
that
Once we got V1, V2, V3, just put everything together. That will give you P. Okay. So this is how you should solve a problem related to diagonalization.
Yes, sir.
All right.
Yeah. And just for this second column, since both of the the values were same. Down, sir. Yeah. Lambda 2. So lambda 1 and lambda 2, it should be opposite. Like if 1 1 others, for the lambda 2 it should be 0 0.
No. So it depends on the condition. Since it said x is your first coordinate and second coordinate should be equal. So that's the only condition you have.
Yes, sir.
Right. You don't have anything on z.
Yes, sir.
Right.
Yeah.
So you just take once z to be 0 and another time z to be 1.
Yes.
Okay. So you will get two vectors. And the top one you can just keep it 1 and this one also can be 1. It doesn't make any difference. So this can be 1 1 1. But what happens is 1 1 0 1 1 1. Both can lead us to 0 0 1. Right.
Yes.
So you just subtract this from this. You will get this.
Okay, got it.
Right. So
Yeah.
but for having more number of zeros, we just put instead of 1 1, I just put 0 0. That's it.
Yeah.
Okay. But linearly independent required. So you should be able to get two linearly independent vectors, eigenvectors. Okay.
Yes, sir.
All right. Thanks. At least I spent some time with you guys. I thought I will finish everything by half an hour and just close.
I can make you wait for one more hour.
No. Don't wait. No.
No.
So that's not what I meant.
No. I'm just kidding, sir.
Okay. All right. Yes, Dhruv.
Sir, can you solve second question also once of this mock?
Yeah. So that's what I said. That is what I thought slightly trickier. So I will solve that. Okay. So the question 2 is basically what I mentioned, which is the nilpotent operator. That's called nilpotent operator. Okay. So the question is the following. So it said, given a linear operator to us from R3 to R3, and this is such that t power 4 is 0. So this is very, very important in the problem. So this is the most important. Okay, so given t power 4 is 0, what they said is, and also the other condition is t is not equals to 0. T is not a 0 operator. Okay, so I hope you guys know what is a 0 operator is, right? Everything maps to 0. So again, it is stated that t is not equals to 0. Non-zero linear operator. Now the question is about what are the eigenvalues. Okay, so that's the question basically. All the options are related to eigenvalues and eigenvectors. So you would have seen this, right? So if lambda is an eigenvalue and v is its corresponding eigenvector, the condition that it should satisfy is the connection between lambda and v is tv should be lambda v. Right? If I take the operator once again, so t of v, what happens if v is an eigenvector? This will be lambda v, right? tv will be lambda v from the previous step. And lambda is a scalar, comes out of the transformation. This will be lambda of tv. And again, tv, since v is an eigenvector, tv becomes lambda v. And this will simply be lambda into lambda v, which will raise to lambda square v. And here, this is represented as t square v, taking transformation twice. T of v is represented as t square. So t square is lambda square v. So like this you can move ahead and you can talk tk of v, t power k of v will be lambda k power v. Right, this we would have studied in one of the lectures. So now what is given is t power 4 is 0. So you have to use this. That means when I substitute k is equals to 4, t power 4v will be lambda power 4v. And you see this is 0. This is 0 for any v. So that means t power 4v will directly be 0. This implies us that lambda power 4v should be 0. Right? And v is an eigenvector. Right? And from this, you can imply that lambda power 4 should be 0. So lambda power 4 being 0 is like lambda 1 is 0, lambda 2 is 0, lambda 3 is 0, lambda 4 is 0. Correct. So all lambdas are 0, which will imply that lambda will be 0. The only possible eigenvalue for this kind of transformation, the operator, is 0. So no other lambda satisfies this condition. Okay. So from there, option A will be done. So 0 is the only eigenvalue. Once option A is correct, option B is wrong, option C will also be wrong. Right? So all three are just like disjoint to each other. So once 0 is the only eigenvalue, eigenvalues cannot be purely imaginary. And at least one eigenvalue is non-zero is also wrong. And eigenvector corresponding to the 0 eigenvalues is a non-zero vector. So that comes from this. When t is not equals to 0, right? And your lambda, when t is not equals to 0, there is a v where your tv becomes 0 times v. Right? So that's when, so this is v is the eigenvector for 0. Right? So we said that it is told that this is not equals to 0. right? And 0 times V will give us 0. All right. So then this transformation, sorry, no, it doesn't require this much of explanation also. So once 0 is an eigenvalue, your null space will be non-zero. This I hope most of you know this, right? So you can note this. So if 0 is an eigenvalue, then null space will be non-zero. Why? Because TV will be 0V, 0 times V, and this implies TV is 0. So there exists a non-zero vector V such that TV becomes 0. That means V belongs to null space. Okay, so that's all for option D. So if 0 is an eigenvalue, its corresponding eigenvector will be non-zero. And the eigenvectors correspond to the eigenvalue 0 are the vectors in the null space. Okay. So in the null space, along with 0 vector, there will be non-zero vectors also sitting in that. Okay. So that's about option D. So therefore option D will also be correct. Okay. So that is about question 2. Is this all right? Any confusions?
Sir,
Hmm.
if 0 is the eigenvalue, then for that eigenvalue, uh, there would be no eigenvector. It will be the matrix itself, right?
That's what. So it will be the matrix itself. So the null space of the matrix will be your eigenvector.
Yeah.
So whatever vector that takes the product to 0 is an null space vector, right? Null vector, right?
Yeah.
So that will be your eigenvalue, eigenvector, sorry. That's what I said.
Okay.
So the vector which takes your transformation to 0 is a null space vector. And once if 0 is an eigenvalue, then when I say V is an eigenvector corresponding to this 0, then definitely T of V should take me to 0 because the right side will become just 0 times V, which is 0. So therefore, the vectors that are eigenvectors to the eigenvalue 0 are nothing but your null space vectors. So vectors coming from the null space.
Okay. Yeah, got it, sir.
Dhruv, is this okay?
Yes.
Okay. All right. So I think this is the only problem that is new to you guys. Rest of the problems are just very straightforward and just uses most of the problems uses formulas that you have learned, formulas and the concepts that you have learned. All right. So then I think that's all for today. So prepare well. Okay. As I mentioned, just focus on the concepts that I have mentioned and solve problems related to that. And also a strong recommendation is solve mock for quiz 2. So if you do these two things, then your chances of getting better scores in quiz 2 will increase. Okay.
Sure, sir. Yes, sir.
Yes. All right then. Thank you guys. Thanks all for joining. And
I had a request.
yes.
It is completely off topic, but okay. So, is there any chance like you can contact to the instructor of this signals and systems? By any
So
chance?
what's the problem?
Actually, the mock of the signals and system is not yet released. We had mailed and messaged on GSpace as well. The whole day we have been doing that, but there's no reply from their side.
Oh, is it? So,
We messaged to Victoria ma'am and the signals and systems this G space thing, everything,
okay.
but there was no response.
So actually, the course instructor for signals and systems is Jashwanti, if I'm not wrong. Just in the G space, just check for the name Jashwanti, and you can tag.
Just a second.
We don't have any direct connections because she is coming from the prof side. So even I'm not
No, sir.
that connected.
We don't have. There's no just one thing in this. We just
Okay.
signals and systems at IITM. That's it. E2101.
Oh,
It was completely headache for us because for the quiz one also there was no this mock.
okay. So have you info? So who are taking the live sessions? How are the live sessions happening?
Actually, because of my offline college, I did not attend any live sessions yet. But
Okay, so ask one of your friends who join live sessions, no? So like, or get a time at least for a minute and try joining that, so that instructor will be available at that time in front of you. So no escape,
okay, and there are
right?
no possibilities from your end also.
See, the problem is I know instructors related to DSP, so you can ask me DSP.
Okay.
So I know instructors related to digital systems, ESTC, etc. So the only problem is signals and systems is coming from professor's side. So one of prof's PhD student is who is the instructor. So we don't have any direct connections with the
Okay.
instructor. So,
Okay. Got it, sir.
so maybe I can
Convey
inform
my.
Victoria
Yeah,
or
please.
convey the authorities. Yeah, that's it.
Yes, please.
Yeah, I can do that from my end.
Okay, that will be more than enough, sir. For because
Okay.
we have pinged her everywhere, message tagged everything we have done, but there's no reply from her end, Victoria ma'am's.
Okay.
Yeah.
Okay, I will check with her, but I think the time has gone past, man.
At least we have
Even
tomorrow's
now,
time. At least tomorrow's time we have.
tomorrow's time is. I agree. I agree.
Yeah. And to ping you on G Space, which it's Shrikant or Chandrakant, sir?
No, no, it's not Chandrakant or anything.
I
It's not even Srikant. It will be like Venkateshan at the rate something. It will be available in G space. I'm in the G space of Math 2.
other
So
sir.
Math 2 September 2024.
Yes, this Shubham sir was there. Shubham Moria.
If you just scroll down, where am I? So just type VENKA. So it's like
Okay, Shrikant
we
Venkat. Yes,
Srikant Venkateshan board. So
yes,
it's
yes,
me.
yes. Yeah.
So you can tag us. Even Vishal is the other instructor. You can tag Vishal also.
Okay.
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 Yeah.
Yeah.
So you can also tag me. I'm not saying you shouldn't tag
No,
me.
no, no, no.
You can
That was
tag
just the
me.
other option.
Yeah.
Okay. Okay, sir.
Yeah. Yeah.
That's all. And
All right, Prithvi, all right, Vishal, all right, Dhruv. Let's meet after quiz 2. Okay.
yes, sir.
Okay, sir.
Hopefully, you guys will do definitely good in quiz 2.
After this session, yes, of course, yes.
Yeah. So, all right. Thanks all. Thanks all for joining.
Yes, thank you.
Thank you, sir.
Have a great day. Bye.
Thank you, sir.
Bye. Bye, sir.